All right, good morning. So we want to finish up the material for this semester. And so I'm on page 254, section 6.2, solving trig equations. So last time we talked about uh, the inverse functions, and keep in mind your definition of a function. For every domain, there's exactly only one range value. On all of those inverse functions, we only get one answer. That's true, period. Today, I'm solving trig equations where lots of other things can happen. And so the first thing I want to think about is the instructions on page 254, and I'll solve perhaps number 12 for us if you want to find that in your book. But the instructions say to solve on the interval from 0 to 2 pi. So let's just talk about the significance of that interval. Brackets and parentheses, right? The brackets mean that it includes 0. The parentheses means that it does not include 2 pi. And the reason for that is because essentially 0 and 2 pi, that's one trip around the circle, isn't it? 0 and 2 pi describe the same location. So if 0 is a solution, then automatically 2 pi would also be a solution. Why do I need an interval anyway? Well, if I don't specify an interval, every time I go around the circle, I pick up more solutions, and I can go backwards or forwards with that to pick up additional solutions. So we want to limit our discussion to one positive rotation around the circle. And again, on these, we may get multiple solutions, and that's okay. So let's look, just for a starter problem, at number 12. So I'm trying to isolate the sign of x, which in this case, I'm going to subtract 2 from both sides. That's easily done. We don't even have to show that, do we? And I'm left with the sign of x is equal to 1. So now the question is, what functions, what values give me a sign value, what angle measures rather, give me a sign value of 1. And anytime we deal with ones and zeros, my mind always goes to the unit circle. And we learned way back at the beginning of the semester that the first value here is the cosine value. The second value is the sine value. So I'm looking for places where the sine is 1. That's only going to happen at 90 degrees. But again, I don't want 8 degree measures here. This interval implies that I want radian measures. So the only answer to this problem is pi over 2. So that's the general idea on all of these. Typically, we get more than one solution on these problems as well. So let's think about that. Let me work a couple that are not on that page. So I'll call this problem star. Let's do 2 sine x plus 1 all equal to 0. So again, I'm trying to get sine by itself. The work is the same as it is in algebra. I'm going to subtract 1 from either side and divide both sides by 2. And so I'm left with this expression. The sine of x is equal to a negative 1/2. So again, I want to think about angles whose sine is 1/2. Maybe don't focus on the negative for a moment. Let's think about just a reference angle. So a reference angle whose sine is 1/2 is 30 degrees. Again, I can't stay in the world of degrees. I've got to get into radians eventually. But I'm going to place that 30-degree angle in quadrants where sine is negative. So where all is sine negative? Well, it's positive in quadrant 1 and quadrant 2. So it's negative in quadrant 3 and quadrant 4. So let me find those values. So a quadrant 3 angle is going to be 180 plus 30, which is 210. And a quadrant 4 value would be 360 minus 30, or 330. Again, I want radian measure out of all of that. So these are each multiples of 30 degrees, and we've talked about this several times. My solutions here are 7 pi over 6 and 11 pi over 6. If you don't remember those degree measures, that's not the end of the world. You can always multiply by a conversion fraction, in this case, pi over 180 to get it into radian measure. Notice again, y'all, that I get two solutions, two places in one trip around the circle where sign is negative. Problem star star. Let's do the tangent of x minus 1 all equal to 0. All right, tangent of x minus 1 equal to 0. And again, that's easily solved. We can add 1 to either side. And so I'm left with the tangent is equal to 1. Let me once more think about reference angles. An angle whose tangent is 1 from my special triangle is 45 degrees. But I need that in places where tangent is positive. So tangent is positive in quadrant 1, which is the reference angle. It's also positive in quadrant 3. So 180 plus 45 more would be 225. Again, in radians, pi over 4 and 5 pi over 4 for those solutions. And listen, we can check all of these on our calculator if we want to. If you punch in the tangent of pi over 4 minus 1, you want to be sure that that's 0. Again, as always, I caution you about putting this number in, because if I put that number in, my calculator has to be in radian measure to be able to do that. So just keep in mind, if you're going to start swapping modes there, be conscious of that and be sure you're in the right mode at the right time. If you want to go back and check it with the degree angles, that might even be an easier method to do that. All right, so let's go back and think about some from your textbook. Number 14 on page 254. Says 2 secant x plus 1 equal to secant x plus 3. So again, I need to isolate the secant. So all of the rules still apply. I choose to subtract 1 from each side, and I'm going to also subtract a secant from each side. And so 2 secants minus a secant is 1 secant, and 3 minus 1 is 2. And so you can solve that problem from there. I don't usually like to think in terms of secants. I think in terms of sine, cosine, and tangent. So the reciprocal of secant is cosine. And so I'm actually going to solve this problem. The cosine of x is equal to 1/2. Again, a reciprocal on both sides. So the game is the same. What angle has a cosine of 1/2? From my special triangles, that's going to be 60 degrees. And I want that in places where cosine is positive. So cosine is positive in quadrant 1. And then it's positive again in quadrant 4. So my angle would be 60 from 360, which is 300 degrees. Again, in radian measure, these are multiples of 60. 60 in radians is pi over 3. So you can think about just the multiples of pi over 3. You can do the conversion. I'll leave that for you to think about. But my solutions here are pi over 3 and 5 pi over 3. So again, the basic solving is not difficult, but we want to look at some perhaps that are a little more interesting. Maybe number 16. So when we solve number 16, the first thing I notice is that it's a quadratic equation. So let me just pause for a second and go back and think about solving a quadratic. So if I have a quadratic equation like so, there's a couple of ways to be able to solve that, right? We can try factoring. I think factoring is a good way. By the way, we've got to have it equal to 0 before we do all this solving and factoring business. So that factors into x minus 2 and x plus 2. And then I'm going to set each factor equal to 0. And solve those equations. So depending on who you had for college algebra, they should have emphasized to you that the exponent dictates for me how many solutions I should end up with. So an exponent of 2 in a quadratic, I'm guaranteed 2 solutions. And again, for that problem, this particular problem, I could have moved 4 to the other side and took the square root. But then it's up to me to remember that I have both a positive and a negative solution there. So either way I go, I end up with 2 solutions. That becomes significant in the world of trig because, again, I should end up with, on most of these, 2 factors. But because functions can be positive or negative in a couple of places, that kind of exponentiates the type and the number of solutions that I end up with. So, for example, number 16, the first thing that I notice is I can subtract 2 from either side. And already I see that I've picked a poor problem, and I'll show you why. I end up with secant squared equal to negative 3. When I go to take the square root of either side, immediately I notice that I can't take the square root of negative 3. That problem, unfortunately, has no solution. That was unintentional. Let's go back and work another type of problem. So I'll call this 16 star. Let's do this problem. The secant squared minus 2 all equal to negative 1. Maybe this will give us a better solution. So I can add 2 to either side, and I'm left with secant squared equal to positive 1. So I'll be able to solve that. And then to do the solving, again, I'm going to take the square root of either side. And just like I mentioned a second ago, whenever I or you put a square root on that wasn't there to start with, we have to account for multiple solutions. So plus and minus 1 there. Once more, I don't tend to think well in terms of secant, so I'm going to think about the reciprocal. But I'm in luck because the reciprocal is also 1 there. So I want to look for angles whose cosine is either positive 1 or negative 1. So again, 1s and 0s, unit circle. And the first value is the cosine value, the second value is the sine value. So it looks like I have solutions at 0 and at pi. So let me think about another problem where we can still factor, but then maybe we get multiple solutions as a result there. Oh, while I'm thinking about it also, we've been using the unit circle. You can't see my unit circle, can you? Let me move my camera over. We've been using the unit circle each time. Listen, I can still, I can even solve these using the sine and cosine curves. So again, that's the cosine curve. Cosine is 1 right there, and it is negative 1 right there. Those are consistent with those solutions of 0 and pi. Let me find us one where the factoring is a little bit different. Maybe number 20. Number 20. And again, on number 20, keep the idea of a quadratic equation in mind. So this is 2 cosine squared x minus square root of 3 cosine x all equal to 0. Don't let the trig get in your way. This is the exact same problem as something of this nature, 2y squared minus 3y. And so again, we would try to factor that. We would get a common factor out of that, and then set each factor equal to 0 like we know to do already. So That's the same thing that's going to happen over here. I've got a common factor of cosine. And when I take a cosine out, I'm left with 2 cosine minus the square root of 3. And again, I'm going to set each of those equal to 0. That's our technique for solving a quadratic, is to set them equal to 0. So over here, I can add square root of 3 to both sides and divide by 2. So what I'm really interested in is where is cosine 0 and where is cosine square root of 3 over 2. So again, let's do the same sort of thing. If I go back and think about my unit circle, that has those cosine values being 0. So cosine is 0 at pi over 2 and at 3 pi over 2, at 90 degrees and 270. Again, in radians though, pi over 2 and 3 pi over 2. And then I need to solve the second factor. So the second factor says cosine equal to square root of 3 over 2. A reference angle for that from my special triangles is 30 degrees. I need that in quadrants where cosine is positive. That's going to happen in quadrant 1 and quadrant 4. And so my solutions, I believe, are going to be 30 degrees and 330. Again, in radians, pi over 6 and 11 pi over 6 for those two solutions. So quadratics work the same way as the others do. If you can factor it, factor it. Set each factor equal to 0. Once in a while, let's say that I had factored something. Let's pretend that I factored something and I got factors like this. Cosine x plus 2, maybe I go ahead and solve that. Cosine x equal to 1/2 and cosine x equal to -2. Y'all, I'm good here. I have an angle whose cosine is 1/2. This one is okay. This one is not okay. This doesn't provide for me any solution. Again, the cosine curve doesn't get any bigger than 1 and doesn't get any smaller than -1. This doesn't even exist. And sometimes that happens in the context of a problem. All right, so for sure, I need you to look at on page 254. Let's be sure and look at 11 through 21, those odds. If it happens to be a quadratic, set equal to 0 first on those. So those are the kind that I'll test you on simply because of time constraints. But nonetheless, I want to look at a couple of other problems with you. Some that perhaps are a little more interesting. Maybe one like number 28. And then you can give the others. I've assigned 5 that are more interesting. But 28 says cosine squared theta equal to sine squared plus 1. And so, if I were trying to solve that, I would do like I've always done. But in this instance, I've got 2 different functions. So somehow I've got to bridge the gap between these functions. And you can turn cosine into sine. You can turn sine squared rather, into cosine squared. It does not matter. I choose to solve and replace cosine squared. And I know that cosine squared is exactly 1 minus sine squared. That's a Pythagorean identity. I don't know why I put that in parentheses, so it doesn't have to be there. So if you're taking notes along with me, erase your parentheses. And so let me gather up like terms. So maybe I add sine squared to both sides. And maybe I subtract 1 from both sides. So I'm left with 2 sine squared, all equal to 0. And then dividing both sides by 2. I'm left with sine squared equal to 0. And again, I'm going to take the square root of both sides. Officially, we get a positive and a negative, but it just doesn't have any meaning in the world of 0, does it? 0 has no sign. So I'm interested in places where sine is 0. So again, maybe I'll use the sine curve now to do that. Doesn't matter. So it's 0 here and here, which is happening at 0 and at 180 degrees. And interestingly enough, in the problem set for number 28, it asks us to solve on this interval. So intervals are important. This interval is exactly the same as the other interval, except this implies my answers can be in degree measure rather than radian. Honestly, I don't know what I'll do on the test. I would be prepared either way to be able to solve those. All right, one more like that. Let's see, maybe... they're all similar. Maybe number 29. Trying to get my camera lined up. Bear with me. Number 29 says cosecant squared minus 2 cotangent all equal to 0. So again, I've got 2 different functions going on. Let's see if we can't bridge the gap there. So cosecant squared is exactly the same as what? Cotangent squared minus 1. Is that identity? That again, a Pythagorean identity. Actually, that's not right, is it? It's cotangent squared plus 1 equal to cosecant squared. So if I reorganize this problem, it's all in terms of cotangent, but now let me get it in descending order so that I can factor it. So cotangent squared minus 2 cotangent plus 1 all equal to 0. And y'all, if that factoring is being troublesome to you, factor an easier problem. That's the problem that I'm really looking at. It works the exact same way. So if I factor that problem, and again, you can go through all your factoring business, I believe it's going to factor into cotangent minus 1 and another cotangent minus 1. So although I have 2 factors, both of those factors provide for me a repeating solution, namely cotangent equal to 1. And so as I've mentioned to you already this morning, I don't like to think in terms of cotangent. I'll think in terms of its reciprocal, which is also 1 in this case. So places where tangent is 1 has a reference angle of 45 degrees in quadrant 1, and then in quadrant 3, what's that going to be? 225 degrees for that. So maybe just take a glance at those that are more interesting, and I can work any of those for you when we meet class again. As I've mentioned to you in class, you are responsible for this material, so it's important that you go through these and come prepared next Tuesday to ask questions about that. So we'll go over this, and we'll talk about our test. Our next test, we'll talk about our final exam, and then take that the following Thursday. All right, have a great day.